Hello class, we are going to give you a clip of lectures, okay, according to uh, the continuing idea of the higher order differential equation, okay. I am preparing, as you see on the screen now, okay, uh, is a complete lecture, okay, of the thing that we cover in class that might be having a problem during the in-class lecture. Okay, so I did prepare all this, and we're gonna review through all of the materials again. Okay, the first page start with I think that you have the link, okay, of this uh, where this document is here, okay, that you see on the screen. Okay, we're gonna start with the first page we call capital I and capital L1. Okay, over here. Okay, and now you see. Okay, it's a review of the classical RL circuit. Okay, where the alternate current circuit. Okay, that you study from the fundamental physics. Okay, and also the first course of fundamental of electrical engineering. Okay. For the alternate current circuit, okay, they contain only one R resistance and one inductance with parameter L, okay, and we identify capital D as the operator of d by dt, the difference, okay, of something over the domain T, and with the input source of this physical system is a voltage source ET, okay, is the alternate current here, okay. You know that the voltage cross the inductance, okay, based on the physical nature, okay, and governing law is L di by dt. So we can replace this as d L sub 1 I 1 t is L di by dt. Okay, and this is and the voltage that cross the resistance according to Ohm's law is I times R. So the first equation here is that the voltage Kirchhoff voltage law. Okay, that R sub 1 plus d L1 sub 1 altogether time I sub 1 t equal to E sub t. Okay, according to the direction of the current that I identify in the pictures. Okay, so you can see that with this, this is a very simple, we call the first order system, okay, because we have the D operator in the equation, okay, and then you can be arrange the term and written in a form like a sub 1 star, okay, I sub 1 time I sub 1 t plus a sub 0 star time I sub 1 t equal to, okay, b sub 0 star time e sub e t. Okay, and you can compare the coefficients. A sub 1 star is L sub 1 times D, and A 0 star is R sub 1, and B sub 0 star is equal to 1. Okay, so this is a classical first order system. And then if we continue, okay, to add one more loop, okay, to this second pictures, okay, therefore you have two current loop pictures, okay, of I sub 1t, okay, and I sub 2t, okay, and the same that we add one more resistance and one more inductance that we call R sub 2 and L sub 2t, according to this picture. And then we can write in the matrix form here, okay, we already explained, and this is the basic concept from physics, okay, second course of physics, and also the very first course of fundamental of electrical engineering. Okay, I'm gonna based on what we call the mesh analysis. Okay, the current, the loop currents. Okay, that of I sub 1t and I sub 2t. Okay, this the content of the matrix is here. Okay, AR sub 1 plus DL sub 1. Okay, time I sub 1t minus DL sub 1 time I sub 2t. Okay, that's the first equation of the left hand side equal to E sub t. No, ET. Okay, E with the domain t. And the second loop, okay, we have minus D L sub 1 time I1t plus R altogether, R sub 2 plus D altogether, summation of L sub 1 plus L sub 2, okay, all this term, okay, time I sub 2t must be equal to 0. Okay, and to solve for the general form of this, I think we showed you in the class a couple of weeks ago. Okay, I'm gonna rewrite it again. Okay, this is based on what we call the Cramer's rule. Okay, therefore you can have a diamond here. Okay, the triangle symbol here. Okay, equal to the determinants of this matrix. Okay, this which is the for 2 by 2. Okay, you can use this diagonal term multiply together these two terms minus the cross diagonal. Okay, here. Okay, these two terms. This becomes the division. Okay, according to the Cramer's rule. Okay, way back to your high school mathematics, and the nominator, okay, of this ratio, okay, have to be, you put the column vectors et and 0 to the first column and find the remaining determinants, okay, which should be et times this term r2 plus d and summation of l sub 1 plus l sub 2 altogether times et. Okay, and if we rearrange the term here, okay, and so I2t also, this one is according to the Cramer's rule, okay, and but just use this column vector of et and 0, put it in the second column and find the remaining determinants, okay. So the first one, you can see that you use this triangle symbol time I1t equal to R2 plus D L1 plus L2 ET. Okay, and then if you rearrange this term R1, R2, and D times D become D squared, becomes second order derivative. Okay, and rearrange the term, okay, you get this resulting differential equation we call the second order system. You can observe that for only one loop, okay, with R and L, you get what we call the first order, okay, differential equation. And when you get two loop, okay, of R and L, RL circuit, okay, connected together, okay, you get what we call the second order differential equation. We use this equation because if you using the regular, the matrix solution in the first place, the I sub 1t and I sub 2t is not independent of each other. Okay, but when you use the Cramer's rule, okay, now the first equation, okay, you can separate it to become the pure second order system. Okay, if you know et, okay, you put et on the right hand side and find the derivative times b sub 1 star plus b sub 2 star times et. You get a new function on the right hand side, so you can get you can find I sub 1t over here. Okay, and we go to the next page. Okay, this one is a 3 loop. Okay, when you continue the third loop here. Okay, we go back to the previous one first. Okay, this one I only find the equation for I1t. Okay, the differential equation. But you can use this I2t equal to L1 d et divided by the triangle's symbol here. Okay, this one you get another differential equation, but you can see that the left-hand side operator is always the same. It's the determinant of this matrix, which is represented by this triangle's symbol. Okay, so the left-hand side always going to be the coefficient of a sub 2 star, a sub 1 star, and a sub 0 star. We're linking it over here. A sub 2 star equal to L sub 1 times L sub 2. A sub 1 star is L sub 1 times R sub 1 plus L sub 2 times R sub 1 plus L sub 1 R sub 2. And A 0 star is equal to R sub 1 times R sub 2. Okay, even for the second equation, it's the same for the element. Just replace I sub 1t to I sub 2t. But the right hand side is different, okay, according to the result from the Cramer's rule. Okay, but this one we only going to derive, you have to find I sub 1t first. If you know I sub 1t, okay, you can use this result to find I sub 2t. But this one you don't need to, because each of these equations is already independent of each other when you use the Cramer's rule. Okay, but you can see that for the upcoming solution, you will see that once you start finding I sub 1t, you can get I sub 2t. Okay, and I sub 3t, you continue the loop of the RL as a cascade function. Okay, so now we go to the three loop of RL, okay, connected in as shown in the figure. And we already showed you that from the mesh analysis of electrical engineering, we can write this governing equation as a differential equation, the first order differential equation, three of them. But the problem is I1t, I2t, and I3t is not independent of each other. And again, if you since the matrix over here, the equation here, the matrix of the left-hand side equation is still in the manageable size of using the Cramer's rule. So we identify this triangle symbol, okay, as the determinant of this matrix. Okay, I already show you here, but just explain this to you. But we not, you know, there's a classic formula from your high school mathematics that you can find the determinants of this matrix. Okay, and then again we can be written down as a function of the operator here. This one becomes the cubic function according for this triangle symbol here. Okay. And you can see that this is the result of finding the determinants of this matrix. Okay, and rearrange the term is over here. Okay, and you can see that I1, I sub 1t, okay, again, you put this right-hand side vector on the first column of this matrix, replacing the first, and find the remaining determinants. You get the formula or according to the Cramer's rule, like here. Okay, you can see that once et00, this column replacing here. Okay, so the determinants, remaining determinant is only et. Okay, and then time the remaining determinant is only 2 by 2 now. Okay, over here. Okay, so this one again, I skip a lot of part, okay, because it's a basic concept that you study, like determinants you already study from your high school mathematics, especially for the size of 3 by t. But only in this example we still work in the symbol rather than any numerical value. Okay, again, okay, we rearrange the term. Okay, this is what you get from the left hand side. Okay, you can see that it's obvious that for the left hand side becomes the second order system. Okay, according to the input function of ET, the source of voltage source over here. But the left hand side, okay, since we have three loop circuit, okay, with I sub 1, I sub 2, and I sub t, when separate independence of each current, okay, in each loop, okay, of RL circuit, okay, you get the third order over here with the just like what we show here, like A0 star. Okay, this we missed the star here. Okay, A0 star is here, R sub 1, R sub 2, R sub 3. A sub 1 star is according to this one in the bracket here. You put it in here, you get the time d I1t by dt, since it's multiplied by d with d, and capital D is d by dt. When you're using this, multiply to, you see, the denominator here. Okay, move here, you multiply I1t. Okay, this one multiply I sub 1t equal to this square symbol, which is over here. Okay, the multiplication term of d to the et on the right hand side, which is the quadratic function according to the d operator. So the replacement is you get here. Okay, I'm going to give you the observation, like, okay, when you have only one RL, okay, one R sub 1, and this one should be L sub 1, you get the left hand side, you get first order, okay, contain one derivative of first order. Okay, the right hand side become constant, becomes zero order, no derivative. But when you have two loop function, okay, two loop circuit, okay, of RL, the resulting for the, just to find I sub 1 first here, the left hand side becomes second order, the right hand side becomes first order. Okay, and now when you move to the three loop circuit, okay, of RL, the left hand side becomes third order, okay, the right hand side becomes second order. So you can see that as you can see the trend that as we adding more loop or mesh function circuit over here, we add another R and L. Okay, suppose we go to the fourth, we go to the for loop, for cascade of RL. Okay, with additional I sub 4 T. Okay, in this picture. Okay, over here. But for the tree, okay, I sub 2, I sub 3 from the tree loop, okay, you can still use the what we call the Cramer's rule, okay, to find the independent of differential equation, okay. But certainly, okay, no matter how the right hand side change, okay, the right hand side always be the second order, but the left hand side become the third order because now you have three three RL circuit connected together. Now we move on to the four, okay, the for loop of RL. Okay, we add one more loop over here, and this is the governing equation over here. Okay, this become more complex. If we continue to use Cramer's rule, the problem is that you need to find the determinants of 4 by 4, which is start a little tedious, okay, especially if you're working on the symbol form, not in any numerical value. Okay, so the technique I'm going to show you here, okay, is kind of pretty straightforward, okay, and it can be very efficient, okay, when you extend to solve this problem, continuing to the higher order where you add the fifth loop or the sixth loop or over here, okay. So at first, okay, I think we showed this a little bit in class, okay, so you might, you listen to what I gave you a lecture, okay, in class, okay, you might familiar with this substitution, okay. I'm going to substitute the diagonal element, okay, of this matrix, okay, equation, okay, for the left hand side, okay, of equation as a sub 1, a sub 2, a sub 3, and a sub 4. A sub 1 is R sub 1 plus D L sub 1. A sub 2 is R sub 2 plus the summation of L sub 1 plus L sub 2. And A sub 3 is R sub 3 plus D times summation of L sub 2 plus L sub T. And finally, A sub 4 is R sub 4 plus D times summation of L sub 3 plus L sub 4. Okay? And it's not, it's quite obvious that you can see that the resulting matrix on the left hand side of the equation is a symmetric matrix. So we identify one element, okay, on the upper diagonal, okay, it's going to be, you don't need to identify, make any replacement or substitution for the lower diagonal, okay. So I'm going to use the D operator, dl sub 1 by dt, we call that b sub 1, and dl sub 2 by dt is b sub 2, and dl sub t by dt is equal to b sub 3. And then since you have minus over here, so you add the minus sign according to here. Okay, so once we make this substitution, okay, we can rewrite this, okay, so to the algebraic equation one by one. Let's look at the first equation first. It's going to be a sub 1 times I sub 1 t minus b sub 1 times I sub 2 t equal to the right hand side now is e sub t, et, no sub the e according to domain t. So if you rearrange the term, you get I2t will be equal, move, okay, equal to A1 times I1t minus ET. Okay, and since I sub 2t, okay, you have B sub 1 multiply, okay, if you want to write just pure I sub 2t, okay, you divided B sub 1 to the other side, okay. So now you can see that we can write I sub 2t in terms of I sub 1t according to this, okay. And then we go on to the second equation. Okay. Second equation become minus dl1, which is minus b1. We have minus b1 times I sub 1t plus, okay, diagonal element a sub 2t times I2t minus b sub 2, okay, because now minus dl2 is minus b2 times I sub 3t equal to 0. The right hand side is 0. So now again you rearrange the term trying to write I sub 3 in terms of I sub 1. But you know that now you can write from the first equation, you can write I sub 2t in terms of I sub 1. You put this, replacing I sub 2t in terms of I sub 1 into this equation. And then arrange the term to write I sub 3t in terms of I sub 1t. Okay, so I think we did this for the in-class lecture, so yeah, it should not be too difficult for you because you can see that a sub 1 times a sub 2 coming from you put I sub 2t here, okay, in terms of I sub 1. You get a sub 1 times a sub 2, okay. And then the other term happen here, okay, minus b sub 1 square, okay, why minus b sub 1 square? Because the I sub 2t already have a division of divisor of b sub 1. Okay, once you want to write I sub 3t, you need to divide them by b sub 2 also. But the term of I sub 1t, okay, times b sub 1, there's no b sub 1 as a division, just like I sub 2t. So you need to multiply on both as a b sub 1 divided by b sub 1. So the part of b sub 1 on the denominator become b sub 1 square. Okay, so now you get, and now you can combine the term of I sub 1t from here, that I sub 1t, okay, you get a sub 1 times a sub 2 according here, and then minus b sub 1 is because this is minus b sub 1 square divided by b sub 1. Okay, so that you can multiply together, so that the divisor is b sub 1. And b sub 2 is moving from trying to write I sub 3t, okay, so you need to divide it by b sub 2 also on both sides, so you get this. And then a sub 2 here, okay, times et, okay, is coming from this term, right? When you write I sub 2t, you get et here, and when a sub 2 multiply I 2t, yeah, they multiply multiply et also. Okay, so now this is the remaining term. So now you can write I sub 3t in terms of I sub 1 and e sub et, okay, and all divided by b sub 1 times b sub 2. Okay, before moving on, I'm trying to be try not to make the formula too complicated. I'm gonna substitute this term a sub 1 times a sub 2 minus b sub 1 square as c sub 1. Okay, so c sub 1. So now I sub 3t is c sub 1 times I sub 1t minus a sub 2 et. Okay, so we move on to the third equation here. For the third equation, okay, you get minus b2 sub 2 times I sub 2t plus a sub 3 times I sub 3t plus b sub 3, okay, times I sub, this one should be minus, minus b sub 3 times I sub 4 3. This one is minus, okay, the next equation already have a correct sign. Okay, so now you put the, you want to write I sub 4 3 in terms of I sub 1t. Okay, so you replace I sub 2t in terms of I sub 1 3 using the first equation, put it in here. And then you replace I sub 3 3, okay, by using I sub 3t in terms of I sub 1 3, okay, over here. And then you can rearrange the term, and you can now, with this equation, you rearrange the term and you can get I sub 4 3 in terms of I sub 1 3. You can see that the divisor becomes b sub 1 times b sub 2 times b sub 3, okay. And this one should have b sub 2 square, because to make the divisor equal b sub 1 times b sub 2 on both terms. And then once you arrange the term over here, you get this. I sub 4 3 is a sub 3 c times c sub 1 minus b sub 2 square times a sub 1 altogether times I sub 1t minus a sub 2 times a sub 3 minus b sub 2 square altogether, okay, times e t, okay, and divided by b sub 1 times b sub 2 times b sub 3. Okay, again, not to make the formula too complicated, I'm gonna call this term, okay, I sub 4 3 is something we call c sub 2, okay, times I sub 1t minus, and this term a2 a3 minus b sub 2 we call d sub 1 times et. Okay, so now you can write I sub 4 3 in terms of I sub 1 and et also, okay. That leads you to the final equation here. the final equation you get minus B3 minus DL3 times I sub 3t, okay, plus A sub 4, which is this term R sub 4 plus D times L summation of L sub 3 plus L sub 4, okay. So this term multiplied by I sub 4 3, and that's what you get here, okay. That's what you get here. Minus B sub 3 I sub 3 3 plus A sub 4 I sub 4 3 equal to 0. And then now you press I sub 3 3, okay, written in terms of I sub 1 t. Okay, this is according to this, okay, according to this formula. And you put it in here. And then now you already have a formula for I sub 4 3 in terms of I sub 1 3. You put this on this term, okay. So now with the final equation, okay, since you don't have a fifth loop, you don't have I sub 5 3, the last equation will only have one single variable we call I sub 1 3, okay. And once you rearrange the term here, you get this resulting differential equation with only one variable I sub 1 3, and you already change the dependency of this matrix equation to a single differential equation with independence of only one response variable we call I sub 1 t, okay. You can see from here, okay, to make this divided b sub 3, okay, equal on both terms, okay, you need to multiply this become minus b sub 3 square divided by b sub 1 b sub 2 b sub 3, and then you combine both terms. For the I sub 1 t, you get a sub 4 times c2 here, and this one you get minus b sub 3 square, okay, need to be square because to make this divisor b sub 3, and then times c1. So this is the operator that multiplied by I sub 1 t equal to, okay, you move to the other side. This one should have a minus sign on the left hand side, a sub 4 times e1. When you move to the right hand side, become the positive sign. And then this term, okay, have a positive sign on the left hand side. When you move here, it become negative sign. You get b sub 3. Remember that this b sub 3 have to be b sub 3 square because you have the divisor to make this divisor equal b sub 1 times b sub 2 b sub 3. So you get minus b sub 3 square times a2. So this is the right hand side for ET. Okay. So next we with this resulting equation, we now need to expand how this term gonna look like. First of all, okay, we look at what is C sub 1 first. Okay. Actually C sub 1, okay, when you look at this formula, okay, C sub 1 is A sub 1 times A sub 2 minus B sub 1 square. Okay. So you can see that this is A sub 1, R1 plus DL1, okay, according to this substitution that we identify in the first place. Okay, this one, A sub 1 is R1 plus DL1. A sub 2 is R2 plus the summation of L sub 1 plus L sub 2. Okay, so this one, A1 times A2. Okay, look at the formula of C sub 1 first. It's A sub 1 times A sub 2 minus B sub 1 square. So you get this, B sub 1 is D, oh, sorry. We're going back here again. Okay, B sub 1 is the operator D times L sub 1. So you get this D square L sub 1 square because you get over here you have B sub 1 square, right? And B sub 1 is D times L sub 1. So square have to be D square L sub 1 square. So this is the result. And you can see that this is a little bit quite similar to what we did before on the you right here, like here, okay? You can see that this term, okay, the divisor of this when you use Cramer rules in the two cascade IL circuit over here, okay? But okay, we try to be generalized. When you add more loop, you know that now we move to the 4 RL circuit connected in series, okay, just like this cascaded. We call this cascaded circuit altogether, okay. So C sub 1 is quite similar to the determinants that we have already found, so we can rearrange the term easily, and it becomes the quadratic equation according to the D operator, okay. And c sub 2, okay, c sub 2 over here is a sub 3 times c sub 1 minus b sub 2 squared times a sub 1. You need to use this c sub 1 resource, put it in here, this is c sub 1, okay, and time a sub 3 is here, r sub 3 plus d times summation of l sub 2 plus l sub 3, okay, and this one is you could have minus b square, b sub 2 square, which is over here, okay, d square l sub 2 square, okay, this is b sub 2 square, time a1 is r sub 1 plus dl1, okay, and from this, if you rearrange the term, okay, you get this, okay, this term, okay, like the zero order term will become r sub 1 times r sub 2 r sub 3, and this one is pretty close, similar to what we done here for the third, for the three connected RL circuit like this. Actually, the diamond sign or the triangle sign here. This one, a sub 1, r sub 1 times r sub 2 t plus d. This one with the cubic function of d. Actually, this function is exactly the same as you get c sub 2 here. You can see that this c sub 2 is exactly the same as this triangle symbol, that when you consider the three loops of RL cascaded connected together, okay, so this is c sub 2, okay, they're exactly the same, but now to write this the final equation here, you need to find a sub 4 times c sub 2 minus b sub 3 squared times c sub 1. You can see that this is the reason why we need to compute c sub 1 and c sub 2. So now this is what you're doing. You're using a sub 4 here times c sub 2 times here. Okay, and you know that a sub 4 is what? You see, r sub 4 plus d times summation of l sub 3 plus l sub 4. This is a sub 4 times c2 is here, c sub 2 here. Okay, minus b sub 3 square, b sub 3 square is d square times l sub 3 square, okay, since b sub 3 is d times l sub 3, so b sub 3 square becomes this times c sub 1 is over here. So again, we need to rearrange the term over here and then subtracting the term here, okay, and I already done it for you, okay, this is the right and correct formula. Okay, the way I'm going to show you a little bit, explain it to you a little bit, that how did I get this result. Okay, the easiest one is here when you have r sub 4 times c sub 2 over here. You get r sub 4 times r sub 1, r sub 2, r sub 3. Okay, you get r sub 1, r sub 2, r sub 3, r sub 4. Okay, for the first order, the d operator here. The d operator, okay, the first one, okay, you need to multiply r sub 4 to this d, or the term that multiply d in the c sub 2. Okay, since the term, the subtraction term over here, you start with d square times c sub 1. C sub 1 starts certainly the quadratic function of d. Okay, so this one start with the quadratic term. For the for the first order term, you can directly use this, okay, coefficients of c sub 2 here, multiplied by r sub 4. And then the second term, you use the first order term here, l sub 3 plus l sub 1, multiply to this constant term in the c sub 2. So that's how the result of this coming out. Okay, you can see that the first one you get l sub 3 times r sub 1, r sub 2, r sub 3. Okay, and then you get l sub plus l sub 4 here times r sub 1, r sub 2, r sub 3. And then the remaining 5 term is according to this term for the c sub 2. Once, because all these terms multiplied by d, when you use these two function multiply together, so this coefficient of d, okay, need to multiply by constant, so they can still remaining to have a first order of d here. So the second term is all the 5 term here multiplied by r sub 4 here. So that's how you get l sub 1, l sub 2, and then l sub 1, r sub 1, r sub 3, and r sub 4. Okay, and then L sub 2, R sub 1, R sub 2, and that time R sub 4. Okay, so it's gonna be this one. Okay, and then L sub 3, R sub 1, R sub 2, R sub 4 here. Okay, and then L sub 1, R sub 1, R sub 3, R sub 4. Okay, have to be here. Okay, and then L sub 2, R sub 1, R sub 3, R sub 4. This one, L sub 2, R sub 1, R sub 3, R sub 4. Okay. Yeah, that's correct. And L sub 1. I think there's a mistake here a little bit. It should be. Let's go back and look at this term. Okay. The first term is L sub 1, R sub 2, R sub 3. L sub 2, R sub 1, R sub 2. Okay. L sub 1, R sub 2, R sub. Yeah. You can see the first term over here is L sub 1, R sub 2, R sub 3. Okay. Okay. So this one should be L sub 1, R sub 2, R sub 3. Okay. So these two terms can be repeated. Okay. So this is the correct term, but this one, the first term should be L sub 1, R sub 2, R sub 3. So when they multiply with this term of R sub 4, become L sub 1, become over here L sub 1, R sub 2, R sub 4. Okay, this one is this term. Okay, but this one should be L sub 1, L sub 3, R sub 1, R sub 2, R sub 4. Yes, correct. And then you get L sub 1. Okay. So one of the term here is it's not correct. This is correct. This is correct. This one should not be here. This one should be L sub 1, R sub 2, R sub 3, and R sub 4. This one should be L sub 1. No, not L sub 3. Okay, it should be L sub 1. Okay. Okay, so this one L sub 1, R sub 2, R sub 3, R sub 4, and you need to change this to L sub 1 times R sub 2, R sub 3. Okay, let's make it conform with this term. Okay. Okay, then now you get this term for the first order t. For the d square here, okay, you need this term, okay, multiplied by c sub 2. Okay. So for the second order term, the d square, okay, once you might use this term d times L sub 3 plus L sub multiply to this one, because d times d become d square. The second one is you have this d square, or this term, the sixth term here, okay, but if you multiply by R sub 4, okay, you still get d sub 2. So this is all the term that contain, okay, within the d square. Okay, you have 5 terms here, 3, 4, 5, 1, 2, 3, 4, 5. And then you have another 6 term here, 1, 2, 3, 4, 5, 6, okay. Okay, 1, 2, 3, 4, 5, 6, okay. 1, 2, 3, 4, 5, 6, okay. And also you have additional term, d square, okay, d square, you have this term multiplied by this, and then this term multiplied by this. Okay, for d, so d to the third, okay, okay, d to the 3 over here, okay, you have this term, okay, multiplied by this one, d, multiplied by r4, and then the second one you have d square here multiplied by dl3 by l4. Okay, so the reason that the previous one over here, okay, let's reconsider again. Okay, d square, okay, you get this term 1, 2, 3, 4, 5, 6, but this one you need to multiply by constant of d, okay, r sub 4. But this term d, okay, you need to multiply by d times L3 plus L4. Since you have L3 and L4, you have to double this. So for each one, L3 time here, okay, you have 5 terms, and L4 time here, you have another 5 terms. This is the first two lines. Okay, but the last one over here, you have 6 terms, but now only 4 terms remaining, because you need to subtract this d square L3 square. Okay, once the C1 over here, okay, you use the C1 over here, okay, which is the quadratic form. Okay, so in the quadratic form, okay, so the constant over here, okay, will cause you the second order term to subtract it out from this one. Okay, it's a rearrangement. Okay, if you spend some time, you can rearrange and check it out over here. Okay, so this, so the last term here, 1, 2, 3, 4, 5, 6 over here is d squared times r4. Okay. Oh no, time L4. Okay. Okay, so this one is d squared, and d to the 3 is this term. Okay, and then the final, okay, d to the 4, okay, become L sub 1 times L sub 2, L sub 3 times L sub 4. So you can see that the left hand side over here become the fourth order. Okay, the right hand side become, and how the right hand side become, as you can guess, you can see the trend that from the previous example, that for the 3 loop connecting, the left hand side become the third order. Okay, differential differential equation. The right hand side become second order, and for this one you can expect the left hand side to become fourth order and the right hand side become the third order. And we go and check how the third order gonna look like. Okay, this one, I think to replace this, okay, you can see that if you extend this type that we are doing here, the term gonna keep longer and longer. Okay, and then you're not gonna be able to write down one page anyway. So we develop something that we're gonna use when the order, when you keep extending the circuit with more and more RL connected, which we'll see later. Okay, so the fifth page here is very important. That we're gonna expand using this technique, trying to reduce the term. We're not gonna show the long, very long term, just like what we are showing on this page. Okay, so you can start from here that we know that C sub 1 is in the quadratic term over here. We already found C sub 1. Okay, C sub 1 actually is here. C sub 1 is a triangular sign here. And then C sub 2 is here. C sub 2 is here. Okay. So what we are doing actually, should be C sub 3. Okay. Instead of writing all this term in a very long form over here, we can cut it short by using this replacement. That, okay, if you write C sub 1 as a sub 2, a0 1 star plus a sub 1 1 star d times d plus a sub 2 1 star times d square, and a sub 0 1 star is equal to r sub 1 times r sub 2, a sub 1 1 star equal to L sub 1 times R sub 2 plus L sub 1 times R sub 1 plus L sub 2 by R sub 1. And A sub 2 one side is a multiplication of L sub 1 times L sub 2. Okay? And also C sub 2 becomes the cubic equation with this substitution and replacement. Okay, this is already, let me check it again. I think that it should fit with this. Okay? This one should be L sub 1, R sub 2, R sub 3. Okay, so the correct one is in here. Okay, so I did make a wrong copy over here. This one should be L sub 1, R sub 2, R sub 3 times L sub 2, R sub 2 over here. L sub 1, L sub 2, R sub 1, L sub 3, R sub 1, R sub 2. And L1, R1, R3. This one, L1, R1, and L2, R1, R3. L2, R1. So this one should be R sub 2, okay, not R sub 1. L sub 1 times R sub 2 times R sub 3. Okay, I made a wrong substitution on this page, but actually the correct one is in over here. Okay, this one. This is the correct one. Okay, so this is once you get C sub 1, C sub 2. If you consider C sub 3 to become this form, Actually, it is a sub 4 times c sub 2 minus b sub 3 square times c sub 1. And then you already make this substitution, okay, to simplify the form instead of writing it as a function parameter of r sub 1, r sub 2, r sub 3, r sub 4, and l sub 1, l sub 2, l sub 3, and l sub 4. Okay, instead of doing that, okay, we simplify this form, okay. So now we add just substitute a sub 4, which is based on this substitution, you can see that a sub 4 is r sub 4 plus d times summation of l sub 3 plus l sub 4. Okay, so you get this, okay, you replace this with a sub 4. But you don't change any notation for c sub 2 accordingly, and also c sub 1 here. Okay, but certainly you substitute b sub 3 as d square, b sub 3 square as d operator d square times l sub 3 square. Okay, and now you instead of rearrange the term just like what we are doing here, we're gonna rearrange the term here first, and then this make a rearrangement an easier one. Okay, since you have a sub 4 here, okay, so zero order have to be multiplied by a sub O2 square. Okay, this is according to the formula of c sub 2. And then for the first order, you can see that you have either r sub 4 times a sub 1 2 square over here. Okay, this one multiply this the first order. And the other one is you get a sub O2, a sub O2 square multiplied by summation of l sub 3 plus l sub 4. Because this one all connected with the multiplication term with d. Okay, so this is the first order. So for the second order, okay, you instead of the previous one, you need to subtract the form, and that make it complicated. But if you write down this formula, okay, you get this one. Okay, the second order, okay, you get r sub 4 times a sub 2 square, which is over here. Okay, and the other term is this one, the first order 2 multiplication of this first order, d times d become d square, which is become just the summation of l sub 3 plus l sub 4 multiplied by a sub 1 2 square over here. And then you subtract the term here, the term that you subtracted, d square l sub 3 square, since you already d square have here. So the first order term have no subtraction, but second order term you start having subtraction of l sub 3 square times a sub O1 square. Because since this term multiplied by d square, so you can d square as a common multiplication here. And then the third term, the third order, okay, the third order become a r sub 4, okay, you multiply by a sub 3 2 star, this one times d square. So this one r sub 4 a sub 3 2 star, okay. And then term d times l sub 3 plus l sub 4, you need to multiply this a sub 2 2 star. Okay, yeah, this one, a sub 2 2 star. L sub 3 plus L sub 4. Why? Because this one have d, okay, multiplied by L sub 3 plus L sub 4, and a sub 2 2 square multiplied by d square. So d square multiplied by d become d to the 3. Okay, so this have a common multiplication term of these, the d to the cubic of d. Okay, and for the subtraction term, you have d square L3 square. You need to multiply by a sub 1 1 star, because to make it the cubic of d, okay, this a1 1 star times d square L sub 3 square. You have this term as a coefficient multiplied by d sub 3. And for d sub 4, okay, you can see that you don't have much term for r sub 4 cannot multiply this to make a fourth order. Only fourth order can be happen when you multiply d times L sub 3 plus L sub 4 times a star 3 2 over here. This one, the cubic of d times d become the quadratic of d. Okay, the fourth order polynomial of d. Okay, and certainly the last term here, you have d square times L sub 3 square. You get a sub 2 1 star d square. If two terms multiply together, d become d to the 4, okay, or the quadratic of 4 of d, okay, and then times L sub 3 square, okay, this one, the coefficient that multiply become L sub 3 square times a sub 2 1 star over here. And then you can call the new coefficient here as a 0 3 star, a sub A sub 1 3 star, A sub 2 3 star, A sub 3 4 3 star, and A sub 4 3 star. This one becomes C sub 3. Certainly the become the fourth order polynomial, okay, of D operator, okay. And then we move on to take a look at the what we call the D sub 1, the D operator, the right hand side, okay, which is the start with D sub 1 here. D sub 1 according to our substitution over here, okay, here. D sub 1 is A sub 2 times A sub 3 minus B sub 2 star. Okay, so this one A sub 2 is R sub 2 plus D times summation of L sub 1 plus L sub 2. This one A sub 3, R sub 3 plus D times summation of L sub 2 plus L sub 3. Okay, you remember that? This one way back from this substitution definition we did on the first place. Okay, so this one minus A sub 2 star. Since B sub 2 star, okay, go back to the formula again. No, B sub 2 square, not star, B sub 2 square. Okay, so B sub 2 square become D square times L sub 2 square, since B sub 2 is D times L sub 2. Okay, so now this look familiar that we did before with R sub 1 and R sub 2. So we can already use the formula of C sub 1, okay, but C sub 1 is with the A sub 1 and A sub 2. This one move to the next one. This one become the new formula here. Okay, so you can have R sub 2 R sub 3 times D times L sub 2 R sub 2 plus L sub 3 R sub 2 plus L sub 1 R sub 3 plus L sub 2 R sub 3. This is the coefficient that multiplied to D, and this one is the coefficient that multiplied to D square. Okay, so we move on. Once you already define the D sub 1 as the quadratic form of the operator, capital D operator, you move on to the D sub 2 here. D sub 2 is here. Okay, we use D sub 2. You can see the C sub 2 come with D sub 1, and C sub 3 have to come with D sub 2. This one is C sub 3. D sub 2 become A sub 4. A sub 4 times D sub 1 minus B 3 square, okay, times A sub 2. So we make this substitution, A sub 4 times D sub 1 minus B 3 square times A sub 2. Make this A sub 4 is R sub 4 plus D times summation of L sub 3 plus L sub 4. D sub 1 we already defined this formula, you put it in here. And then B sub 3 is D square L times L sub 3 square. A sub 2 is R sub 2 plus D times L sub 1 plus L sub 2. And then we rearrange the term just like what we did previously. You get this quadratic equation of the D operator here. Okay, this is the constant, and this is the coefficient times D, and the coefficient times D square, and the coefficient times D to the 3. Okay, again, this is a direct formula just like what we did here. That it's gonna keep getting longer once you add more circuit, and it's not convenient. So we're gonna doing something like this technique that we are doing here. We're trying to simplify the form, and with this technique, you're gonna can keep going to a higher order system. Okay, so we use the similar way that we done with the C sub 1, C sub 2, C sub 3, C sub 4, and so on. This one also, we make D sub 1 as a quadratic equation here. And D sub 2, okay, instead of use a direct substitution here, we're gonna substitute D sub 1 as only the quadratic function, and then we rearrange the term here. Okay, and now the expansion term is toward the end of in this slide. Okay, but the formula have to be here. You just replace D sub 2 by A sub 4. You put A sub 4 here. But then you replace D sub 1 only the quadratic function here. Okay, this is the quadratic B sub 0 1 star plus B sub 1 1 star times D plus B sub 2 1 star times D square. And then this one minus b sub 3 a sub 2 square. This one just a direct substitution. Okay, and then we rearrange the term. You get here you get d sub 2 as a cubic equation. Okay, something similar to what we did with c sub 1, c sub 2, and c sub 3. Okay, but d sub 2 become the cubic equation. Okay, as you know that our c sub 2 also become cubic equation also. If you might recall here, this is become no c sub 2 become cubic equation. Okay, so similar fashion, quite similar fashion over here. Okay, so now once you rearrange term like this, okay, now you get the results here. Okay, for 4 cascaded RL circuit, the left hand side becomes 4th order. Okay, for each of these parameter coefficients that multiply for each term of derivative of I sub 1t, okay, it's according to the substitution that we show you, okay, here. Okay, and the right hand side, okay, that multiply for the input function of ET or the voltage source, okay, become the 3rd order. Okay, that's the resulting here. Okay, just want to show you that with this extension for the very simple first and second order system, okay, if you keep adding the similar structure of the system components, okay, the differential equation keep growing the order in quite have a pattern that you can recognize or you can observe. So now we could go on to the 5th loop, okay, of RL. Suppose that we add another R sub 5 and L sub 5 here. Certainly, okay, the resulting mesh analysis of the matrix equation of I sub 1 to I sub 5 is according to Kirchhoff voltage law, okay, can be written in this form, okay. But certainly this equation is not dependent on each other. If you want to find I1, you need to know I2, I3, I4, and I5. And in order that you can use the classical approach of ordinary differential equation to derive the exact function of this, the resulting of this circuit analysis, you need to do what we did previously. But previously we start with finding the I sub 1t first. Okay, we expect that once you know I sub 1t, you can know that you can observe from the last example that from this example, okay, that we try to write I sub 2t, I sub 3t in terms of I sub 1t. Okay, that is once you know I sub 1t, if you substitute it back, you can find I sub 2, I sub 3, and I sub 4. So this is the way that we're going to do when you extend to the 5th order system, just like what you find in this figure. Okay, we're gonna the first couple of equations is duplicate exactly on what we discussed before. Okay, but now we have I sub 5, okay, additional one, and you can see that from the previous analysis we end up only the last equation here, okay, because we finish it here because we the last equation we don't have I sub 5, we don't have a 5th loop on the circuit, so the last equation finished at the 4th equation. But from here, okay, the 4th equation is not the end. You can continue to the 5th equation. So we recall back that I sub 3t can be written in terms of I sub 1t here, and I sub 4t also can be written in the form of I sub 1t here by extended to C1, C sub 2 over here. This is I sub 4t, okay, and you can see that the equation before the 4th equation you need to add this term. The previous one you don't have this term, you have these two terms and equal to 0 when you have no I5. So you can use last equation to reduce the equation to only I sub 1. Okay, but now you have I sub 5, so you need to use this equation and try to write I sub 5t, okay, in terms of I sub 1t. So this is follow exactly the same way that we already did from the previous example. So I sub phi 3 becomes C sub 3 I sub 1 t minus D sub 2 et. And C sub 3 and D sub 2 we already found. You can see that you find D sub 2 here, okay, and then you find C sub 3 here, okay. So now you just expand here to find I sub 5 and then D sub 2. And once you know I sub 5 and I sub 4 in terms of I sub 1, the last equation is exactly the same analysis that we did on the 4 connected RL circuit that finished with I sub 3 and I sub 4. Okay, so you replace I sub 3 and I sub 4 in terms of I sub 1, and then you get the equation. But when you extend for one more loop of R sub and now connected to the previous circuit, you finish at I sub 4 and I sub 5. So this one is exactly pretty similar to what we did from the previous example. So now you put I sub 4 in terms of I sub 1 and I sub 5 in terms of I sub 1, and then combine the term together. This is the resulting equation. The resulting equation, you get A sub 5 times C sub 3 minus B sub 4 squared times C sub 2 all together times I sub 1t equal to A sub 5 times D sub 2 minus B sub 4 squared times D sub 1 and then all together times E sub et. Okay. Okay, we're gonna call this term the left hand side, the operator that multiplies 1t as C sub 4. You remember that we've already calculated C sub 1, C sub 2, C sub 3, this one becomes C sub 4. The left hand side that multiply to et becomes D sub 3. For the previous one, we use D sub 2. And again, we're going to continue. We're not going to use put all the parameter that we did in the first place that we did here. We're not going to use this approach, but we're going to use this one. Okay, this is a much easier approach, and then it can be extended all along. You can connect it to, doesn't matter how far you go. Okay, so we use this substitution of the analysis, okay, to do this for C sub 4. So C sub 4 is A sub 5, A sub 5 is R sub 5 plus D times L sub 4 plus L sub 5 summation. This is A sub 5. C sub 3. C sub 3 is the quadratic equation of operator D. Okay, we use A0 3 star, A sub 1 3 star, A sub 1 2 3 star, A sub 3 3 star, and A sub 4 A star 4 3. Okay, A sub 4 3 star, and multiply by 1 D square, D to the 3 and D to the 4 respectively, and then minus B sub 4 star, B4 square. B4 square is D square times L sub 4 square. Multiply by C sub 2. C sub 2 is a cubic equation here, and then we rearrange the term. Okay, you get the new function of C sub 4 become, as you see here, become the quintic order. The quintic is mean the order 5. Okay, sorry. We need to go back here. Okay, here. This becomes the quintic, the fifth order polynomial function C sub 4. Remember, C sub 3 is the fourth order, C sub 2 is the cubic, the third order, C sub 1 is the quadratic. Okay, so with this, you can update and find the C sub 4 as the operator of fifth order of derivative, that when you multiply to I sub 1t here, it becomes, resulting the left hand side become fifth order differential relationship, that when you add the equal sign, and the left hand side you expect to be the fourth order. You remember the order, when you extend it, it's gonna, left hand side gonna be more than right hand side by 1. Okay, so we go to the updating for D sub 2 to D sub 3. D sub 3, to find D sub 3 you need to know D sub 2, and D sub 2 you know is a cubic function, okay, previously. So you can expect that for D sub 3 have to be the quadratic function or the fourth order. Okay, so that's quite pretty similar analysis here. D sub 3, okay, will become R sub 5, A sub 5, okay, over here, A sub 5 times D sub 2, and D sub 2 is a cubic, okay, of operator D minus, okay, you can see that minus b sub 4 square. B sub 4 square becomes d square L sub 4, L sub 4 square. And then you multiply by d sub 1. Okay, d2 and d1. And do you know d sub 1 is a quadratic polynomial of operator D. By using this substitution, you get the new d sub 3. Okay, arrange the term. Okay, for each you get become the right hand side become the fourth order polynomial here. Therefore, the resulting equation will be over here c sub 4 times I sub 1t equal to d sub 3 times et. And when you multiply the polynomial term on both sides, the left hand side becomes the fifth order, the right hand side becomes the fourth order derivative. So the left hand side, fifth order derivative of the I sub 1t, right hand side is the fourth order derivative of et, which is the input function. So with this, okay, you end up having this system of differential equation, okay, with higher order. The order keep getting higher once you add more RL circuit, okay, to the network, okay. So now with this, okay, starting having a homework for you that we're gonna do it, okay, and some further clip gonna come out and trying to show you how you're gonna do this homework, and with an extension for you to do it more complex problem for your final exam. So the homework, okay, according to what I have been given lecture so far, is that go back to the 5 loop cascade RL circuit, okay, which is over here. This one, no, this one over here, okay. I'm giving you the value of R sub 1 and R sub 2 is equal to 2 ohms, okay. And R sub 3, R sub 4, R sub 5 is 1 ohm. And L sub 1, L sub 2, L sub 3 is 0.1 Henry, okay, the inductance. And L sub 4 equal to L sub 5 is 0.05 Henry. Okay, so the question we ask you that find I sub 1t, I sub 2t, I sub 3t, I sub 4t, and I sub 5t. If E sub et, the input function, okay, the voltage source that supply, okay, the voltage to the circuit is equal to 100 times sine t plus 50 times cos 2t. Okay, so this is the right hand side. Once your differential equation was established, and you know what is ET, okay, it become this resulting differential equation. You can apply the classical approach that you study from the very first course of your ordinary differential equation to solve for the general solution for I sub 1t. As I told you that along the analysis, you already written down the I sub 2, I sub 3, I sub 4, and I sub 5 in terms of I sub 1. So once you know I sub 1, the remaining function is just can be found by back substitution, okay. And you know that for differential equation, you're gonna end up having some constant parameter multiply or adding up in the general solution. In order to find the exact or unique constant value, you need initial condition. So all necessary condition here, okay, I'm going to set it to 0, okay. It's like your circuit starting with the open circuit, and then at time t equal to 0, you shut down, make a short circuit. So once the circuit is short, the complete circuit work, okay. It's open circuit, so once it's open circuit, so no energy. So when the circuit is short, okay, the voltage start to generate the current, okay. So that's the way to begin that. Previously from the time from the set time at t equal to 0, it started in an open circuit system. But once t start to count or start to collect the data or start to monitor, you reference the time at t equal to 0. Okay, so all necessary initial conditions to find the constant within the general solution of the corresponding ordinary differential equation are all 0. Okay, so this is the first one, okay. And on the next clip, I'm going to show you a little bit that the resulting derivation that we found here, okay, can be easily implemented on the Microsoft Excel once this given value have been given to you. So you can, it means that once this value has been given, you can find a star 5 sub a sub 5 4 star, a sub 4 4 star, the coefficient for the left hand side and the coefficient for the right hand side once this numerical value was given. Okay, and also we're gonna go back to your class of ordinary differential equation, trying to apply the classical approach to derive for the general form of I sub 1 up to I sub 5 3. Okay, so that's the first homework. Okay, if you can follow what I've been telling you and can see the trick, and you're not waiting for the new clip to show, to illustrate how to apply this concept, you can go ahead and do it. Okay, and check it out later. Okay, once the next clip coming out, whether your idea is right or wrong. Okay, the second homework, it can be you. I want to extend for the 6 cascade IR circuit. We're not enough yet, so we are here for the third order, so the fifth order system over here. Okay, but with this similar analysis, if you extend for the 6, 7, 8, and you can see that you can on the next clip, once I show you on the when you use the Microsoft Excel, actually the file is already in this the link here, the link of where you get this document. Okay, if you're interested, you can download that file. The file is in here, yeah, the computing here. You see the first file, okay, or you saw on the screen on the left, on top left most here. Okay, if you are interested, actually this file, using the idea that we cover so far up to this point, okay, up to this one. Okay, but for the second question of derive the result in case of 6 cascade RL circuit, okay, you might take a look at the further document that I add here. Okay, we call the extend analysis for 6 cascade RL. Actually, you should do 7, okay, because the remaining part over here is already well established and well derived for you. Okay. Again, this is, I didn't make correct the mistake. It is between L sub 1 times R sub 2 R sub 3, not R sub 1. Okay, again, this is not correct. L sub 1 R sub 2 R sub 3, not L sub 1 R sub 1 R sub 3. The first term, because this the correct term is here, but this one change R sub 1 to R sub 2. So once you add one more mesh or one more loop, okay, of RL connected, extend it to, now you have a loop current of 6 loop current I sub 1 up to I sub 6. Okay, you can recall the derivation of C sub 1, C sub 2, C sub 3, and then again, well, up to C sub 3. We're not gonna try to derive all the parameter in terms of R sub 1, R sub 2 up to R sub 6, L sub 1, L sub 2 up to L sub 6, because the term is going to be so long and so confused to rearrange the term. So I already proposed to you the easiest way to do is to do like this. Okay, you can see that the C sub 3 is all repeated to what we explained before. So C sub 3 become the fourth order polynomial of operator T. Yeah. And this is the corresponding equation. Okay, I didn't have space for the right hand side, so I moved it here to actually this one, it should be the left hand side, but according to the what illustration on your screen, it becomes the right hand side, and the left hand side becomes the right hand side. Okay, but actually you need to move here to this one, but I didn't prepare good space for it. Okay. So C sub 4, say we can extend to find C sub 4, okay, by extending with A sub 5 and A sub 6. You remember that? Okay, we need to expand this one. Okay, we previously we already identified A sub 1 to A sub 4. Once you have the fifth loop, you have A sub 5 and B sub 4. Okay, you have this one, because previously we already in here. We still have B sub 1 to B sub 3, and then A sub 1 to A sub 4 when you consider the 4 cascaded circuit. For the 5th cascaded circuit, you need to add B sub 4 and A sub 5 here. And also now you have 6 root, you need to extend this to b sub 5 and a sub 6. B sub 5 is d times l sub 5, and a sub 6 is r sub 6 plus d times l sub 5 plus l sub 6. Okay, and the formula continues c sub 4. You can see that once c sub 3 is a sub 4 times c sub 2 minus b sub 3 squared times c sub 1. So C sub 4, all the index move one additional value to. So C sub 4 become A sub 5 times C sub 3 minus B sub 4 squared times C sub 2. You can see that all the index 3 change to 4, A sub 4 change to A sub 5, C sub 2 change to C sub 3, B sub 3 change to B sub 4, and C sub 1 change to C sub 2. This is what they got. And then you use similar analysis that we did before. Now you can get this formula as a polynomial order 5. Okay, C sub 4 is a polynomial order 5 here. And then C sub 5 become polynomial order 6. Okay, 6. Just like what we, this is the exact formula analysis that we are using previously. And then that's the left hand side operator. And D also, we start with D sub 1 is a quadratic function. Make this substitution. D sub 1 and D sub 2 is quite unique in the first place. Still not have the formula yet. We start with D sub 3 here. You can see that D sub 2, because the last term you minus that to be A sub 2. But it becomes the formula start from D sub 3. D sub 3 is A sub 5 times D sub 2 minus B sub 4 squared times D sub 1. Okay. So when D sub 4 change to D sub 3 to D sub 4, A sub 5 become A sub 6, D sub 2 become D sub 3, B sub 4 become B sub 5, and D sub 1 become D sub 2. Okay. So this one also, you remember D sub 1, you need D sub 1 for C sub 2. Okay. You need D sub 2 for C sub 3. And now you need D sub 3 for C sub 4. And now you get C sub 5 for D sub 4. So D sub 4 over here become polynomial order 5. You're going to see that, but for C sub 5 you get polynomial order 6. And this one is the corresponding governing equation for this 6 loop RL circuit connected together. Okay, and also once you get this derivation, okay, again, okay, now you didn't stop at I sub 5 just like previous example. You finish at I sub 6. So we follow the formula analysis that we write I sub 4 and I sub 5 in terms of I sub 1 and according to our substitution. And then you put it in the equation before the last equation, that it was the last equation previously in the previous analysis. But now with the new one, you add one more loop of I sub 6. So this one, instead of finishing I sub 5, you need to minus B sub 5 times I sub 6. And then you replace I sub 4 and I sub 5 in term of I sub 1 and rearrange the term. You get I sub 6 in term of I sub 1. And with this formula, you can get that I sub 6 becomes C sub 4 times I sub 1 minus D sub 3 times ET divided by summation of B sub 1, B sub 2, B sub 3, B sub 4, B sub 5. You can see that since I didn't mention this before, that you might be interested in how the divisors spawn in the equation, because the right hand side is 0 anyway. So once you combine the term with the same division and equal to 0, okay, you can erase, you can move that the divisor out of the equation. This means that only the denominator function term is equal to 0. Okay, so this is exactly what we did previously. So now the resulting equation here becomes C sub 5 times I sub 1t equal to D sub 4 times ET. And D sub 5, C sub 5 we already derived here, okay. They become the 6th order polynomial, and D sub 4 become 5th order polynomial. So once you put it in this equation, you get the resulting 6th order ordinary differential equation of I sub 1t. Again, the left hand side becomes the 6th order equation, and the right hand side is the 5th order. Okay, so once you know the ET function, input function, you can use, now you can derive the right hand side function according to the fifth order here relationship. And then once you know the right hand side function, you can now derive for the general solution of I sub 1. And once you know I sub 1, you can I sub 2, I sub 3, I sub 4, I sub 5. Because all of that already can be written in terms of I sub 1t. Okay? So this is the last sheet that gonna give you on this lecture clip that actually in general, okay, we have done what you call, we start with just one circuit, right? And then two circuits connected together of IL, 3, 4, 5, and 6. But what about if I keep extending it to the n period? Okay? To any n, we call n stages and cascade RL circuit. According, you might say that if n has to be greater than or equal to 4, because for true 3, you already use Cramer's rule to derive the general form. But 4, for n equal to 4, okay, we, instead of we trying to derive the formula going to be very long. Okay, we adapt this technique, okay, trying to simplify C sub j in terms of the, the polynomial function of operator d of order j plus 1, and d sub k, okay, as a polynomial order k plus 1, okay, of the function of d operator, okay, and k is equal to j minus 1. That means that when you consider Cj, d have to be d at the j minus 1. You can see that for the resulting equation, okay, if you have an n stage, n stage connected, okay, you end up, using the c at the n minus 1, sub n minus 1, time I sub 1t equal to d at the n minus 2 time et. When you're using this formula, c sub 1 and c sub 2, this is the exact formula. Okay, this one should be R sub 2, R sub 3, I forgot this. Okay, again, you remember that L sub 1, R sub 2, sum R sub 3 over here. Okay, and then you keep extending this formula to C sub 3, C sub 4 that we already did. You're going to end up can apply. We will show you in the next script that we can use the Microsoft Excel to utilize this, the benefit of this computation structure. We can update you to find the coefficient of this polynomial function of operator d according to the left hand side and the right hand side, so that you can apply this to find the higher order differential equation of I sub 1t. Okay, so this is the main part that we would like to show you, that in mathematics, okay, we start with a small problem, okay, start with small and obvious problem, and we keep extending the complexity of the problem and trying to find what we call a pattern. Pattern is mean that can we get to any exact formula? You can see that in class we spend a lot of time trying to derive the general form, but it's going nowhere because you didn't simplify the computation. If you keep continuing to the system parameter, you're going to end up having a very long formula. Even one page couldn't write all of it. So you need to simplify. Mathematics is an open language that you can find the simplification. So on this lecture clip, okay, we already show you that how you can simplify this this form, okay, and extend it, okay, to a higher order system when you keep connecting the RL circuit to, and it can continue to in the lecture here, okay, in this script, we finish at the 6 connected RL circuit, but you can see now the formula is already there, and it can keep extending to any n stage or n RL circuit connected in series together. Okay, so that's about it for the concluding the lectures of on this part. Okay, in the next clip, okay, we will apply all this concept that we do here. Okay, all the concept that we are doing here, and then we're gonna apply and trying to go back and start solving with the with this homework, okay, that I show you, gonna be here. Okay, there. We're gonna try to solve this problem. Okay, but for the result of the sixth cascade, okay, we already done here. Okay, actually it's almost done. Okay, but still not in a well organized form. Okay, but you might try to repeat it. If you want to do it, you might go for the seventh order or the sixth cascade IR circuit. Okay, so see you in the next clip, and hope you enjoy and understandable about the technique that we trying to show you here. Okay.